Hello, everybody. Tomorrow I won't be able to join you in the classroom, so I recorded this lecture in advance so you don't get behind on the material for this class. Today we're going to talk about electromagnetic radiation principles, which is an expansion of what Dr. Hibbs was talking in the last two lectures. It's about the nature of light. And why this is important, because it will connect with some principles that that affect the nature and the quality of the remote sensing data that we're going to use. So it's important to have a fundamental of the basics, not necessarily in great detail, because this topic can delve very deeply into the quantum physics, but it's important to know the fundamentals of or the characteristics of photons or light particles coming from the sun. Okay, so from the sun, we will have light in different forms. It will come in what we call it at different frequencies or wavelengths. There is a relationship between frequencies and wavelength, and we will see it later in this lecture. But what I want to make sure here is that all light coming from the sun is quite diverse, from extreme or highly energetic photons to lower energetic photons. Like high energetic photons are going to be the gamma rays, that can destroy our DNA in our cells in an instant, to radio waves that we use for microwaves and for communication. What we see with our eyes is a tiny fraction of the sun spectral radiation, but it is why our eyes or life have evolved to focus on this narrow area, is because this is the region, the spectral region, where most of the light or the peak of the sun radiation will occur. So the photons that is going to come from the sun is going to travel through space, is going to interact with the atmosphere, it's going to interact with the surface, so it's going to hit the leaf, the soil, our skin, the roof, the man-made materials. Illuminated, it will bounce back like a ball. It will hit the surface and when bounce back, I will travel through the atmosphere again, interacting with it, and at that point will be captured by the sensor. So Dr. Hibbs showed a simplified version of it, but this is the more complete list of interactions of that photon. So what we have at the very beginning is the solar radiation. That photon will travel through the vacuum of space, virtually unaltered, but as it starts traveling through the atmosphere, these two photons, one will be able to reach the surface, the other will interact with the matter or the particles in the atmosphere. So dust, water vapor, gas molecules. So that light that reaches the surface, it will reach water, soil, vegetation, man-made material, will bounce back and again interacting again with the atmosphere. And in this case, our sensor is out of the atmosphere, but we can imagine this sensor being inside in the case of drones. So we have this photon reaching the camera. Now, there will be other photons that will fall into neighboring areas, and these photons will bounce back. The thing is that the bouncing or the reflection of these photons might happen in any direction. Actually, they will the reflection of the photons falling in a place are going to be distributed in a semi-spherical way, like a Lambertian way, like emitted equally in all directions. So there is a high chance that the reflectance of a photon from a neighboring area, not the area that you are studying, but the neighboring area, will be travel through the atmosphere, interact. Some of them will interact with the atmosphere, but others will reach the sensor. So depending on the sun, the distance traveled by that photo will be larger or shorter. If the sun is at nadir, nadir is when it's vertical at the given location. So it so the larger the path of travel, the more chance of that photon to interact with it. The photons that are, let's say, that interact the most with the atmosphere will be on the blue range, the ultraviolet and high energy wavelength. So we will understand when we call a blue color, green, ultraviolet, near infrared, we will have a list, a table. But it's very complex, the interactions. So not all the photons that come from the sun reach the surface. Not all the photons traveling from the surface will reach the sensor. Not all the photons reaching the sensor will come from the area of interest. There will be some noise, some additional information in every sensor. And that adds a noise in the value of the pixel. So can we say 100% sure that this pixel for this location is the true value? No, it has been contaminated by the information of the pixels surrounding that specific pixel. So energy is present in our universe in three forms. One is by conduction, when you put a pan over a burner and the burner heat up, and by contact, it warm up. The other is by convection, and by convection is that the energy from the sun warm up an object, and that object start displacing or moving, like hot air warmed by the sun moves to a higher elevation, causing movement of colder air. There is a third way, and this is related with photons, where the sun radiation will travel to Earth and adding energy to the objects to which it had contact to. Like, for example, if you go to the beach and you sit on a chair or walking by, you will see that the sun start warming up your skin. So the solar radiation, okay, the visible and the near infrared light is interacting with your skin, causing an increase in temperature. And that's the reason the mechanism of our body to address that increase in temperature is sweat. So the energy can be transferred by the absorption, in this case, not the reflection, the absorption of those photons. So what does it mean? So it means that here in this example, if I have 100 pixels of red light traveling through this path, I will have some of them, let's say 20%, will be captured here in the atmosphere. So I get 80 here. Then if it's traveling again, I will get another 20 trapped here, I got 60. Okay, so if I do the math, I will say, oh, I got 60 and the sun is producing 100. The ratio is 0.6, and that is a wrong ratio. We need to account for the atmosphere absorption, because the true will be that the true value will be closer to the 80 that reach the surface versus the 80 that reach the surface versus the in this case the 60 that was able to live. But we will revisit that later. So in this theory, we have, or in the theory of light, we have to describe the nature of light, we have two models, two mathematical models. Why light is a strange phenomena, cannot be described by a single model. It has properties of a particle, and it has properties of a wave, a probabilistic wave. And each of them relate them to, for example, in the particle model, it's related to the theory of relativity of Einstein. In the wave particle, light, or the behavior of light, is related to quantum physics. So what we need to at least know about this, because it's going to describe something interesting. Light is going to create electromagnetic waves, or the movement of photons creates these electromagnetic waves, or the variations in electrical current that's going to depend on the wavelength. And what is the wavelength, you will say? Well, the wavelength is a magnitude of the photon vibration. What is the photon vibration? Well, a photon vibration will be like, an example will be like a bee. Imagine a bee traveling on a straight line. The speed of the bee will be the speed of light. But the wings of the bee are moving up and down. They are vibrating. The vibration doesn't affect the speed of light, but the wings are moving to support that speed of light. So in this case, the wavelength is a distance, a physical distance in units of distance, meters, feet, that represent the vibration of that photon. So the wavelength is a magnitude of this vibration, and the higher the vibration, that means the faster the smaller the wavelength, will be the photon carries larger amount of energy. The slower the vibration, that photon is carrying less energy. So the typical unit for wavelength is micrometers, is meters to the minus 6, or nanometers. Nanometers, I think, is -6, and micrometers, nanometers is, yeah, micrometers meters to the -6, and nanometers meters to the power of -8. Now, frequency, on the other hand, is the number of vibrations or wavelength that occur on a period of time. in a second, for example. So these will be expressed by a unit called hertz. So if you operate the old radio, you will see that some radio stations always mention their frequency, like I think in Logan, Utah, there is 860 hertz in the AM frequency. There is several radios that always mention their number of frequency, because their radio signal is within a specific wavelength. So to explain it in a better way, photons like the gamma rays, highly energetic, like these wavelength, these photons have a smaller frequency. They have a higher frequency. It's like if we count the waves that pass a location, or that path that occur during a period of time, like a second, we will count many. But other photons will have a longer wavelength. These photons carry less energy. So higher energy towards gamma rays, lower frequency towards radio frequencies. So we're going to classify the photons based on this value, on the wavelength, this measurement distance. And the good thing is that we have tables, or we can develop a criteria to read a number, a wavelength, and to know to which light characteristic it belongs. It belongs to a blue color, green, red, near infrared, shortwave, thermal, just by looking at the numbers. And one of the goals of this class is that you memorize those numbers, because when satellite data comes in, or drone data comes in, there is no information about colors. It's all about the wavelength. So they will tell you, this is an image with 10 bands, and band 1 is this value of frequency in nanometers or microns. The second band is in this value. So you need to be able to immediately recognize, oh, the first band is near infrared, the second band is shortwave, the third one. So there is a table, and we will see it later. So wavelength and frequency are related, and they're related by the speed of light. The speed of light is constant to all photons. That doesn't change. What it changes is the vibration of them. So a multiplication of the frequency and the wavelength give us the speed of light, meters per second. So these allow us to calculate, if we have a short wavelength, we will have a large frequency, and vice versa. So the sun is going to produce why the sun produces all these light spectrum from gamma rays to radio, and why our planet doesn't produce that. It's all about temperature. Our bodies, any object here in the classroom and everywhere, have a temperature above this absolute zero. And the absolute zero, the scale that is used to determine the absolute zero, is kelvins. So the sun is at about 6,000 kelvins of temperature. And the Earth, it's about 300 kelvins. So that the temperature of an object determines what photons or light is produced by an object. So having said that, that means that you and I, we produce photons too, or we generate light. Like our skin is light, not necessarily on the range that our eyes can see, but why there are animals that can hunt at night without, like snakes? Because they don't measure smell, they measure temperature or changes in temperature in the environment. So we produce photons at a much larger wavelength range. So and this causes that we produce photons in a specific range in the thermal and radio range, but not in the blue, green, and red or near infrared range. We will come back to that in a later slide. Now, every object produces energy. What's the total amount of energy that an object can produce? Is related to its temperature. The temperature of the object dictates the amount of energy being emitted. So the Stefan Boltzmann law indicates that if we know the temperature of an object to the power of 4, multiplied by this Stefan Boltzmann constant, it will give you the total in watts per square meter of the energy that is expelled, is generated by that object. So the amount of energy that the sun is going to produce is much, much larger. Remember, it's to the power of 4 compared to Earth, which is in the 300 Kelvin ratio versus the 6,000 Kelvin that the sun is. So let me show you, I think here it is. So the sun will produce gamma and X-rays, microwaves and radio waves. And there is this tiny fraction there, very tiny, that we use to see in this environment. And here comes the numbers. So between 400 and 450, we will have blue, 450 between 500 green limit. There are custom tables, but we will use another one that is more understandable, is easy to memorize, but it will tell us if our sensor is capturing image, is capturing information in a specific wavelength, we will know to what spectral region it's referring to. So I think it's important to mention that now for between 400 and 500 nanometers, 400 and 500 nanometers is called blue. From 500 to 600 is green. Let me see if I can write it here. From 400 to 500 nanometers, blue. 500 to 600 nanometers, green. 600 to 700, this is red. From 700 to 800, it's called red, edge. Red, 800 to 800, it's called red, edge. 800 to 900, it's called red, edge. 900 to 1,000, it's called red, edge. 1,000 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 to 1 from 800 to 1100 near infrared. From 1100 to 2300 is shortwave infrared. From this number to 7,000 by forgetting a zero. This is 2 microns, 7 microns. Okay, this is mid-infrared. From 7,000 to about 15,000 thermal or long wave infrared. Larger than that, radio. Radio is still long wave infrared. So, looking at this chart, okay, we have that the blue color here in this figure represent the blue region, the 400 to 500. Different satellites are going to capture those bands. We have Sentinel-2, Landsat-8, Landsat-7, Aster, MODIS, and this sensor will be able to capture a range in between these two values, a smaller or a larger range. The larger the range, we call it broadband because it is wider. When it's narrow, like in MODIS, we have like 5 cameras for the blue region. Let's call it a narrow band because it's very fine measurement. The same happened with green. The same happened with red. Then we have near infrared here. Here we have mid-infrared. And then we have, based on the numbers we have here, thermal data that some satellites have, like Landsat, Aster, MODIS, but Sentinel-2 doesn't have it. So why the width of these small squares is different? Why there is no a same width, or why we need multiple infrared bands, multiple reds, multiple? It's because every narrow band might be affected differently by the atmosphere and also the surface. So what's happening is, like blue, for example. Blue is a photon with a high level of energy compared with the others in this figure, and is the one that gets to interact most with particles, water, atmospheric gas molecules in the atmosphere. So, but not all the photons in the range from 400 to 500 nanometers interact in the same manner. So, by capturing different bands, we can estimate the absorption of the photons in the atmosphere and allow us to back calculate this issue allow us to back calculate that so we can estimate better the amount of reflection of the surface on the blue band. So they say a similar criteria is followed for MODIS. Landsat and Sentinel are more practical applications, while MODIS is a, let's say, it has been designed for more in-detail studies of the atmosphere and the surface, while Landsat and Sentinel are more like practical applications. What we learn from MODIS or satellites of that nature guides the design of the sensors of like Sentinel-2 or Landsat. Now, also technology available at that moment will affect the bands. For example, in near infrared, if we compare Landsat 7, the pink band, we see that between Landsat 7 and Landsat 8, there is a significant reduction in the band or the range of value that the band is capturing. And this is because the plants tend to behave slightly different along this infrared range. So to capture the best signal, it's better to narrow down the band to a very specific range, closer to the 1000 nanometers. So that it's an improvement on Landsat 8 over Landsat 7. Sentinel-2, they follow the same criteria, although they have multiple sensors that are similar to Landsat 8, but also to Landsat 7. So you might ask, what is that gray drawing in the figure that looks like spikes? It's following a curved behavior, but there has these gray areas and there are these white areas. This is the absorption of photons by the atmosphere. What does it mean? The atmospheric transmission means that the percentage of photons that will be able to travel through the atmosphere in that wavelength. So, for example, blue light, only 30% of the light coming from the sun will be able to reach the surface. Only 30%. The odds are better for green, for red, and for near infrared were about 60. But when we are in the mid infrared, the odds of that photon passing are close to 90, but around the 1400 nanometers, the atmospheric transmission drops to zero. That means that photons that have this wavelength will be completely absorbed by the atmosphere. Zero of them will reach the surface, or very close to zero. So if I have a drone or camera that can measure photons in this wavelength, despite it's a sunny day with no clouds or no shadows, the camera will see only a black image. It's only on these areas, spectral areas, that we have this transmission that we can put the sensors to measure Earth. So that's how, or that's an idea of how sensors are chosen, are designed for measurement of the surface. Going again with the mathematics, what is the important, or what is the wavelength at which the sunlight peaks? Because the behavior of the sunlight is not is not a uniform distributed generation of photons. It has a peak based on the temperature. The curve will look like more like a semi-log curve, which higher values towards the shorter wavelength with a long tail. So the Stefan-Boltzmann equation in a different form allow us to calculate what is that peak of that log normal curve. And the simplification is this, that if we have this constant value, which is 2898 microns times Kelvin, divided by the temperature of the object, will tell us the peak of the the curve generated by the source light. So it's like this. This curve is cut here short, and this has a tail. So we'll see that the sun will have its maximum value peak in the which region? The blue region. So when we see the sky, or when we see the sun in the sky, we see yellow, and this is because the atmosphere interacting with a line of sight with the sun. If we were in space, like an astronaut, and we again look at the sun color is white, not yellow. It is because the atmosphere absorption of photons creates this glass to our eyes that make us see the sun yellowish. Earth has a temperature of 300 kelvins, and that means it's going to have a peak at 10 microns. So 10 microns is, if we look at our table, is thermal. So the bulk or the peak of objects in this planet to emit photons, to emit light that can be captured with the absence of the sun, it's around the 10 microns. That means, for example, if we use a thermal camera, we can see objects at night. We can see animals, or we can detect difference in temperature of the soil and the water and the vegetation, because they're emitting photons, but in a range of wavelengths that are related to temperature, to thermal data. So the sun, it's about 10 microns, is the more closer value zero is 9.66, and the sun will be in this domain, in the 0.8. So so our eyes and the eyes of animals and the plants evolved to take advantage of the peak or the region, the spectral region where most of the light is emitted. Some animals or some plants also uses other regions, like bees uses the ultraviolet region to detect patterns in flowers. Actually, there are specialized cameras that allow you to take pictures of ultraviolet, and a flower. We can see a white flower. In the ultraviolet light, the flower has patterns like tattoos. It's very, very interesting. Ultraviolet mapping is kind of hard, because remember the amount of photons that pass at blue, we are in 20%. So the ultraviolet is here in the 300 to 400. So we have very little photons traveling from the sun to the surface that again has to bounce back to the camera. So the camera has to be still. We have to do a long exposure picture, and that limits the capture of that data. But it's very, very interesting. There are some satellites specialized on that, but the pixel size is like half a kilometer, so we don't see the flower status. So as we move through this presentation, the particle model of electromagnetic energy or theory of light uh, describes light as objects without mass, but that as an object can interact uh, with other objects depending on their properties. So as then let me go back here. Yeah. So light also can be considered an electromagnetic wave. No, and this wave is related to the quantum theory. But in this case, the photons or these particles of light are related to an amount of energy. So if we have the Planck constant and we have the frequency of the light, we can measure the amount of energy that that photon is putting through when it hits a surface. For example, if we have uh, an amount of reflection, or if we have a blue light at 400 nanometers photon, we multiply by this constant, which is very small, we will have the amount of energy produced that photon. So by knowing the amount of reflectance, for example, the relative amount that is the photons arriving from the sun and being reflected by the surface, we can sum all the energy that has arrived over the surface and sum them all and call this amount of energy the total reflectance. And also is called albedo, is the total amount of reflection in all wavebands of a surface. So this particle model of electromagnetic energy, again, is going to relate frequency, is going to relate the wavelength, it's going to relate the quantum energy. So the amount of any photon is going to be inversely proportional to the wavelength and vice versa. So the larger this wavelength, like in the radio or thermal, the less energy that photon has. So let me pass this slide. This is for you to read later. But how light is created? And light is created by absorption. If a photon or atom that has electrons that are excited and then lose that excitement, like when it's passing current, electrical current, a photon of light is emitted from that atom. The opposite happens when the electron is at a lower state and is excited. The light can be absorbed by that photon. So this is the photoelectric effect, and this is how solar panels work. So the solar light hits the silicon cells in a solar panel, and the electrons jump to a higher state. And with that jump, an electron is generated and then is collected by the architecture of the solar panel. So the continuous heating of photons produce this continuous generation of electrons that then are organized in electrical current. Now, different elements, when excited, are going to produce different light, different photons in different wavelength. So sodium, the atom of sodium, when absorb an electron or the electrons are excited, will produce photons in very specific bands. The same happens with hydrogen. We have the 400, 500, 600, 700. So neon will produce the white light that we get, the fluorescent light. It's producing photons in the blue region, in the green, yellowish, and red. So the mix of all of them produces that white color. But you see that sodium produces mostly on the in the interface between green and red. So these colors, the yellow colors, are going to be very dominant in this as a light source from this element. So let me show you here. I think I have it here. Yes. So this sodium lamp that we put when we pass current photons through the bulb lamp, it will emit photons in different regions, but mostly in the yellow, orange, red color, or in the interface or the transition between green and red. And that's the reason we get this coloration. So this is how light and electricity relates. And this is also how cameras are going to work. So if a photon of a specific wavelength hits this camera sensor, the camera sensor pixel, that pixel is going to create a tiny current that is recorded. So the amount of photons that hits, let's say we have a wall that is painted half black, half white, and I take a picture that my picture is half white, half black. So in that picture, very little photons of red, green, blue are going to come from the black. So little electricity, little current is going to occur from each of those pixels that capture the black area. But for the white area, I'm going to have a larger current occurring every pixel, and that will be recorded. So if now the white part is changing tones of white from white to gray, so different levels of current will occur to every pixel in that range of white to gray color. And that's how we are going to relate the amount of light being reflected from the surface to an electronic sensor. So we will basically count the intensity of the light, or we will measure the intensity of the light hitting that sensor. So there are, for example, when you have a photographic camera, if your camera is in a low settings, the light might be on a very long exposure, like allows light to pass to the camera sensor for a long time. The sensor can saturate. So in sensors, we limit the time at which we let light pass to the sensor. It's very fast. The the amount of time that the camera opens and closes for scientific applications is one millisecond. In 1 millisecond, we let the light pass through, especially for drones. The longer it is, the exposure or the camera length is open, it will produce blurry images because of the sensor moving at high speed. So these are, again, tables that we will come back to that later, but that's what I wanted to share with you today. I left for you some questions in the Check Your Understanding. So see if this material helped you to resolve. Otherwise, I'll check with you on Thursday when I'll be in class. Thank you and see you soon.